What's up, everybody? In this video, we're going to cover USACO's 2018 February contest at the silver level, problem number 2, snow boots. It's winter on the farm, and that means snow. There are N tiles on the path from the farmhouse to the barn, conveniently numbered 1 through N, and tile I is covered in Fi feet of snow. Okay, so tile 1, 2, 3, 4, 5. There's individual tiles. Each tile has some amount of snow, which is represented by the Fi number. So tile 1 has F1 feet of snow, tile 2 has F2 feet of snow. We're going to be describing later the snow amount is like 0 feet of snow, 3 feet of snow, 2 feet of snow, and so forth. So that's all this is setting up. Farmer John starts off on tile 1, first tile, tile 1, and must reach tile N, which is going to be the last tile, whatever N is, to wake up the cows. Tile 1 is sheltered by the farmhouse roof, and tile N is sheltered by the barn roof. So neither of these tiles has any snow. But to step on the other tiles, Farmer John needs to wear boots. Okay, so no snow on the first one, no snow on the last one, and then on the middle tiles, who knows what we're going to encounter. In his fall weather backpack, Farmer John has B pair of boots, numbered 1 through B. Some pairs are more heavy duty than others, and some pairs are more agile than others. In particular, pair I, so whatever boot pair it is, lets Farmer John step in snow at most SI feet deep, and lets Farmer John move at most BI forward each step. So basically, then we're going to have boots, and they're going to be described by pairs of numbers. For example, 4, 3 would describe a pair of boots that will go up to 4 feet deep, and you're able to move up to 3 steps forward. Unfortunately, the boots are packed in such a way that Farmer John can only access the topmost pair at any given time. So at any time, Farmer John can either put on the topmost pair of boots, discarding his old pair, or discard the topmost pair of boots, making a new pair of boots accessible. So you've got these boots are going to be stacked up in a bag, 4, 3, 1, 2, 5, 6. At any given time, you can either switch to the top layer, whatever the top level boot is, or you can throw that away, which makes the next level accessible. And incidentally, if you've already tried this problem and you're stuck on test cases 4 and 9, you are allowed to skip boots. This will come up more later. But as you work your way down through the bag, you don't have to use every pair of boots. And even if you're not able to use a pair of boots on the tile you're on, for example, if I'm on a depth 3 tile and I have a pair of boots that can only go to depth 2, I can still throw those boots out. I don't have to switch to them in order to switch to the next one. So that's not a dead end yet. You can keep digging through until you hit the bottom of the bag. Here we go. So Farmer John can only, they're going to talk about this right now. Farmer John can only change boots while standing on a tile. If that tile has F feet of snow, both the boots he takes off and the boots he puts on must be able to withstand at least F feet of snow, with the exception of any boots you throw away. If you throw away boots, you don't have to put every pair of boots on. You can discard them without wearing them. Intermediate pairs of boots, which he discards without wearing, do not need to satisfy this restriction. Says it very clearly right here. But a lot of people do seem to have trouble with this. So what's going to happen then is as you're switching boots, if you want to switch to a boots and make forward progress, you need to make sure that the square you're leaving and the square you're arriving at both are a depth that you can stand on with a pair of boots. But if you're just throwing boots out, you don't actually have to check how deep they are, and they don't have to be compatible with the tile you're on. Help Farmer John minimize waste by determining the minimum number of pairs of boots he needs to discard in order to reach the barn. You may assume that Farmer John is initially not wearing any boots. Input format. First line contains 2 space-separated integers, N and B. N is how long the pathway is. B is how many pair of boots you have. The second line contains N space-separated integers, where the ith integer is Fi, giving the depth of snow on that tile. So we were talking about this is like F1, F2, F3 is just the depth on square 1, the depth on square 2, the depth on square 3. That's what those numbers 0, 2, 8, 3, 6 are all about. The next B lines contains 2 space-separated integers each. So here's 2 integers, here's 2 integers, etc. The first integer on the line I plus 2, it's plus 2 because we're skipping the first 2 lines, so line 1, line 2. So starting from line 3, boots 1 is on line 3. So the first integer is SI, which is the snow, the maximum depth of snow allowed by those boots. So this first pair of boots can step up to a depth of 2. The second integer on line I plus 2 is DI. That's the maximum step size for pair I. I guess that's dexterity. I don't know why they choose D. Distance, probably distance I. It's guaranteed that 0 is less than or equal to SI less than or equal to 10 to the 9th, and 1 is less than or equal to DI less than or equal to N minus 1. So basically they're saying that DI Less than n minus 1. Oh, they're saying that the distance of boots can't possibly be longer than the entire path. I don't think that has any impact on the code because you can always stop short with a pair of boots. But they're specifying that the distance a pair of boots can travel will not be. No, I guess that means you can't do the whole thing in one step, can you? Because you can't jump from the start to the end. Less than equal to n minus 1. If n was 5 and my distance was 4, I would be able to go 1, 2, 3. No, I could do it. Okay, so it is possible to do the whole thing in one step if you have a boots with the same distance as n minus 1, because then 4 steps would take you from 1 to 5. They're just saying it won't be greater than the length of the path. The boots are described top to bottom order, so pair 1 is the topmost pair of the bag and so forth. Output format should consist of a single integer giving the minimum number of boots Farmer John needs to discard. It's guaranteed that it would be possible to make him to the barn. Okay, so we don't have to worry about it being impossible to go to the barn. So let's kind of just eyeball this. So 0, 2, 8, 3, 6, 7, 5, 1, 4, 0. Okay, and these are all single digit numbers. I start off with pair 2, 3. And just remember 2 is the depth and 3 is the distance. 2, 3 is the distance, 2 is the depth. Okay, so we can go up to 3 steps, which means potential places we can go are here, here, and here. After taking those steps, we can take further steps or we can change boots. Now, there is a rule, remember, where if you're going to switch to another pair of boots, you have to be able to wear both pairs on the square. So just as an example, even though I can go to 2 and 3, I don't necessarily want to go to 3. In this test case, I would, but what might happen is maybe I've got a pair of boots that only goes to depth 2, but has a very long distance. If I were to say, for example, if my second pair of boots had a depth of 2, but then a distance of, let me see, 1, 2, 3, 4, 5, a distance of 6. If, for example, my second pair of boots was 2, 6, then my first pair of boots, if I went up to 3 steps, actually that wouldn't matter anyway because that's a depth of 3. Let me see. Let me see if I can come up with an example. Okay, let's ignore this sample problem for a second because I want to point out an important dynamic. Let's say like my first set of boots is allowed to wear up to depth 3 and can go a distance of 3. My second set of boots is only allowed to wear to a depth 2, but can go a distance of, what did I determine? 1, 2, 3, 4, 5, a distance of 6. Okay, so starting here, I could go to this square, or this square with a depth of 3. If I were to go to this square, then I would not be allowed to put these boots on because these boots can't stand on the square that has a depth 3 of snow. But if I stopped on this square instead, even though it's not as far, then because of the fact that this 2 is less than or equal to the depth that the second pair of boots can wear, I can switch to the second pair of boots, and from there I can travel 6. So this is one of the things that trips a lot of people up as well, is it looks like you should be able to just be like a greedy algorithm, but a greedy algorithm is not going to work on this because there are going to be situations where you want to stop earlier on a smaller number to switch to a specific pair of boots that won't be able to go as deep. And there are a lot of test cases that cover this, where you'll have a pair of boots that can get you quite far, but actually you needed to stop sooner to switch to a pair of lighter boots that can go further so you can make a big jump, and you wouldn't be able to switch to those boots necessarily a later step. So back to this starting problem though. So my first boots have a depth of 2 and a distance of 3, which means I can go here, here, or here. I can't go here though because I only can go a depth of 2. I also can't go here. So on the first step, my only option is to go to this location right here. From here now, again, still can go a distance of 3, which means potential places I can go are here, here, and here. But I only have depth 2 on these boots. So actually I can't go to any of those positions. So I'm stuck, which means I have to throw these boots out. Next pair of boots can go to a depth of 4 and can only go a distance of 2. So I've discarded 1 pair of boots. I'm now on the 4, 2 boots, 4 depth, 2 distance. So if I were to go distance of 1, distance of 2, that would be okay. I can get to that location because then I have depth 4 and that's larger. So depth 4, distance of 2. I check here and here. Neither of those will be able to wear these boots. So now I need to switch to a pair of boots that has at least a depth of 3. So I throw the 4, 2 boots away. Next boots are depth of 3, distance of 4. Let me rewrite this here. Depth of 3, distance of 4. So because depth 3, I'm okay. Distance of 4 means I have options to go here, 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 and here. This is only depth 1, so that'll let me get 3, 4 to there. And then I can get to the end. So I've discarded the 2, 3 boots. I discarded the 4, 2 boots, and I finally made it to the end with the 3, 4 boots. So at the core, what we've got with this problem is a situation where I have some number of boots and I have some number of tiles. I'm just going to kind of generally draw these tiles. I have some number of boots. I'm going to say boot, 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 boot. Okay, so I start off with the first boot on the first tile, which always has a depth of 0. Depending on the distance of this boot, there are places that I can go, or I can choose to discard these boots. It's possible I might not even use the first pair of boots right off the bat. I may want to discard. So at any given moment, you have the choice of either discarding a pair of boots or taking some number of steps forward to a tile that you're able to step on. And then every single turn will work this way, where you can either move forward or you can change boots. This lends itself to a recursive problem. Then what you would do is for any given state, you would have one recursive call where you throw away the top pair of boots and change to another pair of boots. And again, you'll have to check to make sure you can wear those boots before proceeding. And then also you would have a loop where you would check for every distance. If you can step on that square, you'd have a recursive call to that distance. And while that's fine, and that's a decent algorithm, this actually is a really good excuse to introduce some basic dynamic programming. Most people are a little nervous about dynamic programming. It's kind of difficult to do, but this is actually a pretty easy problem to do dynamic programming on, and it gives a pretty gentle introduction. So the way that dynamic programming is going to work on this is very similar to memoization. Basically what you're doing is you've got every square. So let's say square 1, square 2, 3, 4, 5, 6, 7, 8, 9, 10. Those form columns, and you've got every pair of boots. I'm gonna one index these as well. Boots 1, boots 2, boots 3, boots 4. And essentially what this is a Boolean array to tell whether or not it's possible to get to a particular location with a particular pair of boots. So square 1 has a depth of 0, and the original boots you start with always can stand on square 1 no matter what. So we're going to start with a true here. Now what we're looking to do is we're looking to try and fill out this chart. And we're going to fill out this chart by trying to figure out, using these boots, boots 1, which is 2, 3, looking forward, what places can we get to? And likewise, considering the depth of tile 1, which is 0, what boots can we change to? And we're just going to fill out the chart from top to bottom. So imagine like you're standing on square 1 wearing boots 1, and you're trying to think of where you can go to. So we'll check tile 2. Tile 2 has a depth of 2. I potentially can go there because my depth of my boots is 2. So that would be true. And also because 2 is less than the distance 3 from the last true that we've seen. So I would mark this as true. Square 3 has a depth of 8, which I can't stand on, so it's going to be false. Square 4 has a depth of 3. These boots only go to 2, so that's also false. And then 5, 6, and 7 also are too deep, so 5, 6, 7. Now square 8 is only a depth of 1, and our boots could stand on that because our boots go up to a depth of 2. So what we're going to do then is we're going to see, are we within 3 squares of a true? Because if we're going to get to square 8, which is a depth of 1, we would need to be able to arrive at one of these squares with the pair of boots we're currently wearing. So we look back a total of 3 steps. We check here, 1. If we were to go 1 step from 7, we could get there, but we can't get to 7 with boots 1. We could go 2 steps from 6, but we can't get there. We could go 3 steps from 5, we can't get there. In fact, the last square we could have met would have been square 2. And square 2 to square 7 is square 2 to square 8 rather is too far. So square 8 is also going to be false. Mark a false there. And in fact, if you use some clever bookkeeping, you can realize that once you've gone more than a distance of 3 from a true, everything on that whole line is going to be false just because you can't get to it anymore. And then so that's what you can do with boots 1. With the first pair of boots, I can go to square 1, I can go to square 2, but everything else is either too deep or too far. So now I go to the next line, pair of boots 2. Now, pair of boots 2 in square 1. Question, can I wear pair of boots 2 on square 1? In order to be able to do that, the depth here would have to be less than the square 1, which it is. And then also, I would have to have been able to reach square 1, which I can look up here and see I was able to reach square 1. Because of the fact I was able to reach square 1, and that's a given, but later on it won't be. Because I was able to reach square 1, and because this pair of boots is able to stand on that tile, then I can mark this as a true. So I can get to square 1 with boots 2. We can move forward from here. Square 2. because of the fact I could stand on square 2, that means, and because of the fact square 2 has a depth less than 4, I could wear the boots on square 2. Likewise, I can check up or I can check left. And you don't have to check both. The first check you want to do, though, is checking up. If I look up and I say, okay, well, I was able to stand on this square before with an earlier pair of boots, then that means that I can stand on the square with this pair of boots. If I'm not able to stand on it with an early pair of boots, that's what I need to check to see if I could step to it from a previous square. Okay, so 3 has a depth of 8. I can't stand on there, so that's false. 4 has a depth of 3. I can stand on there. So with a depth of 3, a depth 4 boot would be allowed to stand here. But I look up, I didn't previously have a way to reach this tile. If I previously had a way to reach this tile, I could just switch into these boots. But because I didn't, now I have to check and see if I could step to this tile. And because these have a distance of 2, I can check 2 squares away. So that would be this tile and this tile. If either of those is a true, then that means that I can leap to this location, and it is, so I can. True. That indicates it's possible to get to tile 4 with boots 2. If I can get to tile 4 with boots 2, let's see where else I can get. Tile 5 is a depth of 6. Tile 6 is a depth of 7. Both of those are going to be too deep, so that's going to make a false and a false, like that. And then tile 7, depth of 5, that's going to be a false. Tile 8 with a depth of 1. I could stand there, but we've already gone more than the depth of the boot, the distance of the boots. The boots had a distance of 2. From the last time we had a true, we've gone a distance of 2. You can check this again recursively, or you can just check this in retrospect with a for loop. So if I hit a value here, I can do a for loop back 2 squares to see if either of those is a true. Or again, you can set a flag to false and indicate that you've gone out of range of the boots. But either way, these are all out of range because if you look back 2 squares from 8, there's no trues. If you look up from 8, there's no true, which means I couldn't reach square 8 with boot 1. It also means that I couldn't get to square 6 or 7 with boot 2. And if I can't do either of those 2 things, then I can't get to square 8. So this also is going to be a false. And then the rest of these are just going to be falses all the way down. So that's how far I could get with boots 2. So I'm getting closer. I made it to square 4 this time. So now boots 3. Boots 3 has a depth of 3 and a distance of 4. So because I can get to square 2, and incidentally, you don't need to only check the square above. If, for example, and it's not the case, but if, for example, this was a false, but this up here is a true, I still could switch into these boots. It doesn't have to only be 1 square up. You have to look all the way up. And I'll come up with a test case, hopefully, after this that'll show how that works. But you don't have to be on wearing the immediate pair of boots to switch to the next pair of boots. It's just if any of the boots above you is true, and the pair of boots that we're inspecting here is capable of standing on the square, then it'll be true as well. That's going to be the same case here. Tile 2 has a depth of 2. The boots we're wearing go up to a depth of 3, so which means I can switch into these boots from an earlier pair of boots. The third tile is a false. That is a depth of 8. I can't stand on it. Here, depth of 3. I could step on this tile, so I check up. I see that it was possible to make this tile with an earlier pair of boots, which means I don't need to check to the left to step to it. I can just get to this tile with boots 2 and then change into boots 3. So that puts a true there. Here, depth 5. This is going to be 6, 7, and 5. Those are all going to be falses. False, false, false. Okay. So now we're to that 1 that we keep encountering. If we look up from this square, we have never been to this square before, which means we can't change into these boots after reaching square 8, which means our only option is to step to square 8. Because our distance is 4 on these boots, we check back 1, 2, 3, 4 squares to see if we can find any trues. And since we found a true, that means that we can step to square 8. Square 9 has a depth of 4. The boots only go to a depth of 3, so that's false. Square 10 has a depth of 0. We have never reached square 10, so we can't change into boots. We can't change into these boots. So we can check up to 4 squares behind. 1, 2, 3, 4. We encountered a true here, which means that we can, if we can get to square 8 with boots 3, then we can step to square 10 with boots 3, and that becomes a true. Now, as soon as you hit a true in the last column, you're done. And whatever your index is, if you're 0 indexing this, if this was index 0, 1, and 2, and 3, then it would be the index. If you do decide to 1 index this, then it just would be 1 less than this number because you start with boots 1 and then you arrive at boots 3, which means 3 minus 1 is 2. You've discarded 2 sets of boots, and that's the output. So I mentioned earlier being able to skip, and I want to come up with a slightly different problem. I'm just going to change the boots around and see if I can demonstrate how that works. 8, 3, 6, 7, 5, 1, 4, 0. Okay, so my goal is I want to make it so that you have to stop at this square and then change to boots that reach this square. I was kind of demonstrating that a little bit earlier. 1, 2, 3, and 4. Boots 1, I'm going to have be 3, 3. I like that. 3, 3. Boots 2, I'm going to have a depth of 2, but a distance of 1, 2, 3, 4. It was 6. And then these don't even matter. I'm only going to need the 2 sets of boots. So we'll just do those. Okay, this is just to demonstrate needing to stop. Let's actually demonstrate needing to skip a pair of boots as well. Let's do the second pair of boots. This will be 2, 6. Second pair of boots can be 2, 4. 2, 3, 4. Yeah. Okay, this is good. This will show a couple different edge cases here. Okay, so my first boots are a depth of 3 and a distance of 3. Second pair of boots are a depth of 2 and a distance of 4. Third pair of boots are a depth of 2 and a distance of 6. Yeah. Okay. So first pair of boots, this is always going to be true at a depth of 0. To get to here, I can get to that because that's 1 step back. So that's true. 8, I can't even stand on. For this one, 3 is within the realm of the first boots. So I can check 3 squares back. 1, 2, 3. There's actually 2 trues in there. I only need 1 though, which means that I can get to that square. True. 6 is too deep. 7's too deep. 5's too deep. 1 is not too deep, but if I check back 1, 2, 3 squares, I don't have any trues, which means that's going to be false, false, and false. So I can't get there with boots 1. Boots 2. Let me think. I wanted to have a pair of boots. Let's do depth 1 on these second pair of boots. I want to illustrate boots that you can't use. Okay, so it is possible to get to this square. True. But we can't get to the second square because it's too deep. Actually, we're not going to be able to hit any of these squares because this is depth of 1. So I did that on purpose to make these all false. So we'll go false all the way across. False, 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 false. This is technically not too deep, but it's too far. So that's still going to be false, false, and then also false. Again, not too deep, but too far. All right, so that puts us on the next set here, 2, 6. This will be true because we can switch into those boots. Now here, I mentioned this before that you can go 2 steps up. I want to switch into a pair of boots that goes to a depth of 2. My immediate previous pair of boots was a depth of 1, which means it was not allowed to step on the square. But I am allowed to change into these boots because if I look all the way up, there was a previous pair of boots where I was allowed to wear those pair of boots. And if I could get a pair of boots to this square, then I can change into a later pair of boots, skipping a middle pair of boots, even if that boot doesn't go deep enough. So that puts it true here. That's going to be the same for this square right here, actually. Oh no, it's not. Sorry, this is the other edge case I wanted to test for. This one here is a true, which means that I can arrive on this square, but I'm not able to change into these boots because this only has a depth of 2. So even though I was able to reach the square before, I can't change into these boots, which means I do have to check this way. I have a distance of 6, which means as long as within the past 6 I've got a true, I can step here, and that's fine. This true happens because I can step here from that square, not because I've arrived here and I can change into the boots, because I can't do that. Oh wait, sorry, this is too deep. So I can't even step here anyway. False. So even though I could go with a pair of boots, I can't change into these boots because these boots are only depth 2, so don't go deep enough. This is false because it's 6, 7, 5. Reaching here, I've never reached this square before, so I can check up to 6 squares back. 1, 2, 3, 4, 5, 6. I found a true, which means I can step to here from that previous square. That's true. False, too deep. And then once again, true because there's one within 2 steps back. So that's your dynamic programming approach. Basically, you're filling out a chart. For any given square, you can reach that. For any given square and any given pair of boots, given some location, you can reach that square if either, assuming you can even stand on the square with the pair of boots you're considering, if either you had a previous way to reach those that square, no matter how many sets of boots ago it was, or within the distance here, if there was a square you could reach, then that means you can step to it. And just so again, that's the dynamic programming solution. And just briefly again to show you if you want to do the recursive solution instead. Essentially, what you've got is you've got some sort of recursive function that has your current tile number, which you start on tile 0, and your current boot number. I'm going to 0 index these 0 and 0. So what we want to do is we want to check to see if these boots cannot step on this index, then we can't do anything about it because we can't get here with that pair of boots. If they can, if these boots are deep enough to step on this index, then we have 2 recursive calls. One recursive call is we're going to do the boot index plus 1, just to say like, okay, let's skip these boots and see what happens. And actually, let me think. I think you can always skip the boots. Yeah, whether or not it's deep enough, you can always try to skip the boots. So that's going to happen first. Assuming our boot number, assuming we have boots remaining, we can do boots plus 1 with the next pair of boots with the same tile, and then we'll check to see if the boots have the proper depth. Then we'll make a for loop for 0 up to whatever the depth of the boots are, and we're going to try and do the recursive function call with that, whatever that I is for that for loop, plus our starting location. I did boots first, didn't I? I should do same pair of boots, B, and then current location, whatever, X plus I. So this is the general structure for the recursive formula. Given some recursive call, assuming we have boots left, we can go ahead and make the recursive call with the next pair of boots, and skip this pair of boots. And then also, assuming we can wear this pair of boots on this tile, then we will try to step forward to every potential future square we can get to using that same pair of boots. And again, then basically for every tile, you're either throwing away boots or trying to step forward, and you're going to have a recursive call for each of them. If any of these is true, if this is true, or if any of those is true, that indicates that you've reached the end. Then you would just return whatever your boot number is. So this has to be an integer return type. So basically, if any of your recursive functions, whichever recursive function returns true, you probably want to do the if depth first and then the boot skip second, because we don't want to skip boots and then get the later number. We want to try and move forward with the current boots. If we can move forward with the current boots, then that would be the answer. Otherwise, we would try to skip the boots, and then that would be the next answer. So I switched the order of these two. But basically, yeah, that's the recursive approach. Is you try every possible step forward. If any of them get you to the solution, you return the number that you were given. If none of them do, then you skip the pair of boots and then make a recursive call on the next pair of boots, and you'll do that for every single square. And it's basically the same thing. The algorithm is more or less the same, and I think it runs in the same time complexity. It's just a matter. No, I think there's going to be overlap with the dynamic programming. Then there's only going to be one way to reach any given square, or one time you visit any given square. But with the recursive problem, there might be 2 different ways to reach a certain square. Like you might step forward and then switch boots versus switch boots and then step forward. So if you do recursion, you have 2 different paths to get there. With dynamic programming, it goes straight across and only does it one time, and that should be a little bit more efficient. But yeah, either one of those methods is fine, and that's the algorithm. So good luck coding it, and I will talk to you on the next one.